一个人哦，然后我是硕士班3年级，然后跟高中一样的是过4样主要然后我是跟张树成老师。
你是几年级的？
哦，硕3这样子。
硕3，好。
我现在在读是 K2 还有密蒙马路
OK， 很好。好，那我们要开始哦。那这一边的就下一次自我介绍，好不好？OK，Lecture 20。Now Lecture 19应该只是 the Vey algebra, because I only talked about the Vey algebra. Okay, and now I will talk about the Vey model and the Cartan model. So since the Vey algebra has the same cohomology as a contractible space, it can be an algebraic model of the total space E.G. Okay. E.G. is contractible. And then what would be a model of M? Say, let M be a left G space. Right. Which algebraic object has the same cohomology as M? Or the Deram theorem says that the cohomology of M can be calculated using the complex of differential forms, right? So an algebraic model for the cohomology for M is the Deram complex. Okay. Let's see infinity forms on M. Oh, so M is a left G manifold. Okay, and then an algebraic model for the Cartesian product is so if you how do you compute the cohomology of the Cartesian product? Right. the tensor product, right? We're using real coefficients, okay? So you don't have other terms, it's just a tensor product. So it would be the Weil algebra tensor with the de Rham complex of M. Mm-hmm. And then an algebraic model for the homotopy quotient, which is EG cross N divided by the diagonal action. It's the base of this. Okay. This is a fiber bundle, a principal bundle over the homotopy quotient. And so you want the forms in the, you want the elements coming from the base, so it's going to be the basic elements of this. Okay, so now, okay. Now, well, let me make a definition. Yeah. Say, just a minute. Yeah. So let's say if script A is a G differential gradient algebra, okay, then the horizontal elements are defined to be the elements such that IA is 0, right? So it's the set of all alpha in A such that IA of alpha equal to 0 for all A in the Lie algebra. Yeah. If it's a G differential gradient algebra, then it has interior multiplication. And so horizontal elements make sense. Okay? And then invariant elements the invariant elements are those such that the Lie derivative is 0. Okay. That's assuming that G is connected. Assuming that the group is connected. Okay? Mm-hmm. And then the basic elements are elements that's both invariant and horizontal. So it's basic elements. IA is 0 and LA is 0. Okay. That's a definition of basic elements. We know that if you have a principal bundle, then the basic forms upstairs are precisely the forms that come from the base. Okay? Okay. So now, both the Weil algebra and the Run complex are G differential graded algebras. So they have those three operators, D, interior multiplication, and the Lie derivative. Okay. Each one of them has the three operators, and then you can extend it to the tensor product. Right? So, so we can extend D and IA to the tensor product as antiderivations. Okay, so what it means is that if you have say alpha tensor beta, then this is defined to be d alpha tensor beta plus minus 1 to the degree of alpha times alpha tensor d beta. Okay? So, and similarly, you extend IA as an antiderivation, and you can extend the Lie derivative as a derivation. Okay, so this makes WG tensor with omega n into a G differential gradient algebra. Okay. And so it makes sense to talk about the basic elements in this tensor product. And, well, this is just heuristics, you know. It's like, it's reasonable that this is an algebraic model for the homotopy quotient. And so the equivariant Run theorem says that for a connected Lie group G and a left G manifold M, the cohomology of the homotopy quotient, that's equivariant cohomology. The equivariant cohomology of M can be computed from the cohomology of the basic elements of WG tensor omega n. Oh, okay. Okay. Now, okay, for this to make sense, yeah, I have to show that this is a subcomplex, right? So we need to show that D takes basic elements to basic elements. So, proposition. Now that's true in general. So if A is a G differential gradient algebra, then D of a basic element D of basic elements are in basic elements again. Okay. So suppose alpha in A is basic. Okay, then I want to show that IA of D alpha is 0 for A in the Lie algebra. Okay, now can you see why this has to be 0? IA of D alpha. I know that IA of alpha is 0 because alpha is basic. Yeah, because IAD is the Lie derivative minus DIA. Okay? And because alpha is basic, its Lie derivative and its interior multiplication are both 0. And then I also have to show that LAD alpha is 0. Well, that's because LA commutes with D. You see, LAD is equal to DIA plus IAD. DD is 0, so this is DIAD. And that's the same as DIAD plus DIA. And so that's DLA. Okay? So the Lie derivative commutes with D. Okay. DLA alpha. And that's 0 because alpha is basic. So it's invariant. Okay? And yeah, so D alpha is basic. Okay? And yeah. So that says that the basic elements form a subcomplex. Therefore, you can compute its cohomology. And the theorem is that if you compute the cohomology of the basic elements in WG tensor omega m, you get equivariant cohomology. Okay, so this is the equivariant round theorem, and I hope to prove it, not right now, but at the end of the course. Okay, so let's first do some other stuff with it. Let's try to do some calculations using the equivariant round theorem. Now, this complex is called the Weil model. This is called the V model. Okay. Okay, it is not the simplest model. There's another model called the Cartan model. Okay. Yeah, but let's see. Well, let's see what the theorem says in the simplest case. Okay. So example. So let's take M to be a point. G acts on the point trivially. Okay? Then the equivariant cohomology of a point, right, that is the cohomology of the homotopy quotient of a point. So you take EG cross a point, and then you divide by G. EG cross a point, it's just EG. So EG over G is BG. Okay. So the equivariant cohomology of a point is the cohomology of the classifying space. Now, by the equivariant Deram theorem, then the cohomology of the classifying space, it's the cohomology of the V model, which is the V algebra tensor, well, omega of a point. That's just, yeah, what is the omega? What's omega of a point? It's just R, right? It's just the constants. There are no differential forms. So you, and this is tensor over R. So if you tensor R over R, you just get the V algebra. Yeah, so it's the cohomology of the basic elements in the V algebra. Okay. Compute it with respect to D. Now, well, let's try to work out the basic elements of the V algebra. Oh, just a minute. No, I think yeah. Yeah. So the okay, so the V algebra, it's in terms of a basis. It's the exterior algebra on the theta tensor with the polynomial algebra on the U's. Yeah, so you see every element of the Weil algebra, there are only finitely many of these monomials in the thetas, right? So every element of the Weil algebra can be written as the sum of, well, it's going to be this, right? It's going to be some A1 theta 1, AI theta I, okay? No, just a minute. It's going to start with, okay, A0, which is a polynomial in the U's, plus AI theta I, okay, plus Aij theta I theta j, and then the largest monomial in the thetas is theta 1 to theta n, A1 to n. Okay? Where the A's are in this polynomial algebra. Right? Mm-hmm. Mm-hmm. Yeah. Yeah. So, yeah, you see, right, everything in this exterior algebra, it's a linear combination of monomials in the theta. But each theta can occur just once, right? Because here you're taking the wedge product. So if you have the same theta, theta 1, twice, the wedge product is 0. Okay? So here, you see, these theta i's are all different. Okay? So every element of the Weil algebra can be written like that. Okay? Now let's look at the horizontal elements. So alpha in the Weil algebra is horizontal if and only if IA alpha equals 0 for all A in G. Yeah. Now, what is IA of A0? Pardon?
The constant of the polynomial.
Now, A0 is a polynomial in the U's. Okay? So it starts with a constant term, then it has, monomials in the U's. But what's IA of a constant? 0, because IA reduces the degree by 1, right? A constant has degree 0, so IA of a constant has degree -1, so it's 0. IA of a constant is 0, okay? And then IA, what's IA of U? Any U? 0, right? By definition. So IA of a monomial in the U's is also 0 because it's an antiderivation. Therefore, IA of A0 is 0. Okay? So because IA of a constant is 0, and IA of any UI is 0. Okay. Yeah. Okay, now what is IA? Now let's see. Let's do IXJ of AI theta I. Yeah, what is this? Yeah, it's AI times delta IJ, right? Because XJ and theta I, they are dual bases, right? And so this will be AJ, okay? That's right. But you see, if you apply IA to this whole thing, okay, this term is going to give you a constant. Because that IA, it's going to kill one of the thetas. So this will give you a constant. This will give you what? It will give you, it's this IXJ is going to kill one of the theta. So you'll be left with one theta, okay, in each term. And then 2 theta, then 3 theta, and so on. See? So, and that's a basis. The theta i's form a basis. So, yeah. So this if IA of alpha is 0, and this is your alpha, okay, then IA of each one of them has to be 0 because they can't cancel each other out. So this has to be 0. Okay? You see, if any of the AJs is not 0, then it is going to be in IA of alpha. Okay? And so IA of alpha won't be 0. Okay? And then, well, let's just maybe just do IX1. So what's IX1? A sum of AIJ, theta I, theta J. Well, you see, you can write this as A1J theta 1 theta J plus AIJ theta I theta J, where I is greater than or equal to 2, right? And this, when you apply it here, what do you get? 0. Everything will be 0 because there's no 1 here. Okay? And then if you apply this to this, x1 applied to, this is x1 applied to theta 1 gives you 1. So you're going to get A1j theta j. And x1 applied to theta j is 0. So that's what you get. Okay? And yeah, so that's what I said earlier. If you start with 2 thetas, after you apply Ix1, you'll end up with just 1 theta. And there's no way that this term can be canceled out by these other terms. So this is going to be 0 if Ix1 alpha is 0. Okay? And that says that all A1j's is 0. Yeah, so if you have a horizontal element, then all the AJ's are 0, all the A1J's are 0. There's really nothing special about this 1. All AIJ's are 0. And similarly, all these other coefficients are 0. Okay? So you can do an induction, but by induction, so alpha is horizontal in the Lie algebra if and only if, what is your conclusion? Your conclusion is that all of these coefficients are 0, except the first one, right? Because that's automatic. IA of A0 is 0. Okay? So if and only if alpha is equal to A0, and that is a polynomial in the U's. Okay? So what is the set of horizontal elements in the Lie algebra? What is the horizontal element in the Lie algebra? I mean, if it's a horizontal element, then it is simply a polynomial in the U's. Okay? So those are the horizontal elements in the Lie algebra. That is just the symmetric algebra of G dual. Okay? And yeah. Now the basic elements are the horizontal elements that's invariant. So it's the invariant polynomials. Okay? And therefore, by the equivariant de Rham theorem the cohomology of BG, which is the equivariant cohomology of a point, okay, is the cohomology of, oh yeah, no, just a minute. So then I still have to calculate D. Yeah, so the cohomology of BG is the cohomology of the Weil model with respect to D, and okay. So I guess that's all we can say at this point. I think it's going to turn out that this D is 0 on the invariant forms. So that the final answer is just this. Okay? But at the moment, I don't see why the D is 0 on this. All right. But we'll figure that out later. Okay, now a simpler model than the Weil model is the Cartan model. Okay, so I'm going to derive the Cartan model for a circle action first. Now, for a circle action, the group is S1, so the Lie algebra of S1 is R, isomorphic to R. And then, so let X be a non-zero element of the Lie algebra. Then it's a basis, and theta is its dual basis for G dual in the exterior algebra, and U is its dual basis in the symmetric algebra. Okay. Then the Weil algebra is lambda theta tensor RU. Okay. But lambda theta, it has basis 1 and theta. Okay. And so this is RU, direct sum theta RU. Okay, so in an element of the Weil algebra is A plus theta B, where A, B are polynomials in U. Okay? And let's now work out the horizontal elements and the invariant elements. So A plus theta B in the Weil algebra. Just a minute. That's the Weil algebra, right? And then we have to tensor with omega n. Yeah, no. Let's just a minute. Sorry. Let's erase this. Okay. So you have R of U plus theta R of U, and then you tensor over R with omega n. Okay. Now, so R of U tensor with omega n. That means, see, this is a polynomial in U, and when you tensor with omega n, you simply replace the real coefficients by forms, right? So you'll get omega n U. That's this tensor with this. And then this tensor with this is theta omega n U. Okay? So these are elements of the form A plus theta B, where A and B are elements of omega m U. They are polynomials in U with coefficients in the forms. Okay? And then A plus theta B is horizontal if and only if Ix of A plus theta B is 0. And you only have to use one x, because all the other elements of the Lie algebra are multiples of this x. Okay? And so let's work this out. Ix A plus theta B, it's Ixa plus, okay, what's Ix theta B? What? Yeah, you need to apply the anti-derivation rule. So you'll get Ix theta, that's 1, so you get B, and then minus theta IXB. And that's 0. And so that says this is constant. This has to be 0. This is no theta, right? So this has to be 0. B has to be minus IXA. Okay? And then if B is minus IXA, this term is automatically 0 because you have IX. Okay? So that's the condition. And so, so the horizontal elements are A plus theta B is horizontal if and only if A plus theta B is equal to A minus theta IXA. And that is 1 minus theta IX times A for A in it's a polynomial in U with coefficients in the forms. Okay? So, okay, I'm going to stop here. So we have determined what all horizontal elements look like. And then, so this is part of the way in simplifying the Bay model. And next time we'll continue with this to get the Cartan model. Okay? Okay, so let's stop here.